Okay, Assalamualaikum and a very good day to all. So I'm going to continue for this one, topic 10, Faraday's law of inductions. Okay, before this we discussed about induced EMF, how the induced EMF is actually produced. Okay, basically it's because of changing of magnetic field. Okay, and then we also discuss about the relationship between Faraday law of induction, where the Faraday law states that rate of changing of magnetic flux induce an EMF. Okay, rate of change of magnetic flux induce an EMF. Okay, so that's why we actually come up with the equations before, where it's going to be EMF equals to negative d flux B over dt. Okay, negative over there is to represent the induced magnetic field that need to be produced to oppose the original change in the magnetic flux. And then we go to the Lenz's law. Okay, Lenz's law is about we produce the changing of magnetic field. Okay, change of magnetic field going to produce induced current, and this induced current are going to produce their own magnetic field, which this magnetic field passing through a given area, which actually we call as a magnetic flux, or we can call as a induced magnetic flux. And this induced magnetic flux are going to oppose the original change in the magnetic flux. Okay, so means that the change of magnetic field are going to produce an induced current, and this induced current are going to produce their own magnetic flux, or we can actually magnetic field that oppose the original change in the magnetic flux. Okay, so we are going to proceed with the next one, which is EMF induced in the moving conductor. Okay, so let's proceed with this one. Okay, as you can see that before, we need to understand that there's a three-way for to have induced current, or we can actually induce an EMF. Okay, which is one of it is going to be change of magnetic field. Okay, one is change of magnetic field. Okay, and then we can change the area. Okay, area what? Area of the loop that the magnetic field going to pass through. Okay, change of the area of the loop that magnetic field can pass through. And the last one is going to be the orientations of the loop. Okay, so increase and decrease of magnetic field, or actually it's more better that we call as the increase or decrease of magnetic flux going to affect the directions of the induced current. Okay, we are going to use what? Right hand rule. Okay, so in front of you we have what we call as this one rod that actually moving to the right, which you can see that is going to increase the magnetic flux. Okay, so when this thing actually increase, what about the directions of induced current? Okay, use the right hand rule, FIB. Okay, FIB. Okay, or here we can actually FIB, or we can actually use the FVB. Okay, because inside this rod definitely there are going to be electrons, so okay, V, and the magnetic field here is towards you, and definitely you are going to get that the directions of force going to be, okay, so the directions of force going to be V B. Okay, so directions of force going to be downward, okay, based on your right hand rule. Okay, so what happened is okay, so means that what happened is when you actually use the concept of the first thumb rule, okay, so right now I want you to find the directions of the induced current, okay, because basically it's increased in terms of magnetic flux. So the directions of the magnetic field now is actually toward Earth. So because increase is going to be opposite, so the directions of induced current going to be same thing, which is clockwise motion. Okay, so these directions of induced current are going to oppose the change in the magnetic flux, which is right now we can see that the magnetic flux is increased. Okay. Okay. So now we are going to okay, what if we change rod into an electron? Because as you can see that the flow of electron, the flow of current is basically the flow of electron. Okay. Okay, so now we have a rod, but here inside the rod we have an electron. Okay, so example, if I didn't give it to you the directions of force here, so please find by yourself. Okay, so we are going to use the right hand rule also. Okay, so the V over there for the electron, remember we have to change the directions, which is to the left, and then the directions of the magnetic field is toward Earth, so the directions of the force going to be upward. So what happened is, example, if the rod doesn't connect to the U rod like previous picture, okay, so what happened is the flow of electron going to be in counterclockwise. Okay, so from this picture you can actually see that all the electrons are going to accumulate at the upper part, and definitely the positive charge are going to accumulate at the bottom part. So the directions of the conventional current going to be clockwise, and the directions of the electron flow going to be counterclockwise. Okay, so as you can see that even though it doesn't as you can see that the change of magnetic flux here is because of electron basically cut the magnetic field over here. That's why they are going to have the change of magnetic flux, which is definitely there's going to be a change of magnetic flux, they're going to be induced current. Okay, so we are going to find the formula for the moving conductor, or we can actually find the formula for the EMF induced for the moving electron. Okay, so here we are going to do two methods, which is one of the method is basically using Faraday law. Another method is using without Faraday law. Okay, so I'm going to show the first one. Okay, as you can see that before this we have a picture like this, and then we have U over here, and that is going to change into, and then it's moving. Okay, so what happening is going to increase the area of the magnetic flux, and then it's moving with some velocity over there. Okay, so from here we can actually get that V equals to dx over dt. So means that this, okay, the rod is going to change, the rod going to move with velocity, which definitely are going to move with some distance over time. Okay, and then because you can see that it's going to change the amount of area that magnetic field can pass through. So that's why we are going to have a dA equals to L ds. Basically, you're going to get here is L square, but ds here is the distance that the rod moving, okay, and L is this one. Okay. Okay, so you are going to put this equation into this one, so you are going to get dA equals to L V dt. Okay, so we are going to find the formula for the induced EMF that relate with the moving conductor. So this is the relationship of the moving conductor. So based on the formula of the Faraday law, EMF equals to negative d flux B over dt. Okay, so EMF going to be okay, the B, the magnetic field not going to be changed. Is going to the B value here is quite constant. Okay, the change of the basically the change is the magnetic flux. So you are going to get here is a B dA over dt. Okay, so you are going to put this one into this one. So you are going to have EMF equals to B L V dt over dt. So you cancel out the dt. At the end, you are going to get the formula as a EMF equals to B L V. Okay. So this is the formula that use the Faraday law. How about the formula without using a Faraday law? Okay. Okay, so I'm going to show you without using a Faraday law. You are going to get the same thing. Okay, so basically here, okay, you can see that the electron is actually moving upward because there's a there's a force actually make it electron moving to the upper part of the rod. So we can actually relate with the F equals to QVB. Okay, remember the force acting on the charge that moving inside the magnetic field. Okay, so since V perpendicular to the V, then definitely electron are going to feel a force. Okay. Okay, so like I mentioned before, the electron flow going to be in counterclockwise motion, and the conventional current going to be clockwise motion. Okay, so right now we are going to relate with the F equals to QVB. Okay, so you can see that for the electron to move, definitely they need to have a work done. Okay, so work done equals to force times distance. Okay, so you put the force here into this formula, then you are going to get QVBD. Okay, so D over here, I'm going to change it as L. Okay. Okay. Okay, because L, okay. Okay, so because why is L? Because the electron moving inside the rod, so this is L. Okay, so you are going, okay, so in chapter 4 we have this one formula where V equals to energy over Q. So V is EMF here, U is work done over Q. Okay, so you put the work done over here, and then definitely you are going to get QVBL over Q. So you still are going to get EMF, or best is actually more specific is induced EMF equals to BLV. Okay, so you can use any method for you to prove. Okay, and then basically you are going to get the BLV also. Okay, got it? Okay, let's proceed with the next one. Okay, so like I mentioned before, the change of the magnetic field, or more specifically the change of the magnetic flux, going to produce an induced current, which means that is going to produce induced EMF. Okay, you can understand that induced current is movement of electron. How electron actually move inside the wire? Because there's a attractive force and attractive and repulsive force inside the wire. So basically, electrons are going to move in this direction. Okay, repulsive force by negative here and attract by the positive here. So the electric field is moving from positive to negative. So means that that's the reason why, when electric current flow in the wire, there's an electric field in the wire that does work to move the electron. Okay, so now we are going to relate the change of the magnetic flux to the induced electric field. Okay, so this result applies not only to the wires and other conductor, but it's actually a general result that applies to any region in space. Okay, so this is we call as the Faraday law, general form. So in the previous chapter, we have this one formula, which is VBA equals to negative EDL. Okay, do you remember this formula? Okay, so we only focus on this formula. So we have here is we change to the EMF. So we get EMF equals to closed loop EDL. Okay. Okay, so this formula is basically the formula that relates electric field with the potential difference. Okay, so we are going to relate it with the induced electric field, change of magnetic flux with the induced electric field. Okay, so you have this formula, and then I think you already understand that we have a Faraday law formula, which is EMF equals to negative d flux B over dt. So we are going to combine these two formula. So we are going to get the formula is EDL, the induced electric field, equals to the change of the magnetic flux. Okay, so if you look at this part, this formula are going to integrate in the closed loop. Okay, so now we are going to find only the area that have a change of magnetic flux, only the closed area that have a change of the magnetic flux. Okay, so the EDL here going to focus only on the area that have a change of magnetic flux. Okay. Okay, so therefore, so I think it's better for us to proceed with the example so you can actually understand more about it. Okay, so this one going to be your formula that you are going to use if the question state about the change of the magnetic flux that induce the electric field. So this is basically the formula. Okay, let's proceed with the example. Okay, so this is the example, and the question state here is a magnetic field between the pole face of an electromagnet is nearly uniform at any distance over a circular area of radius r0. Okay, the current in the winding of the electromagnet is increasing in time. So when the current increasing in time and the B change, definitely you are going to produce an induced current, which is definitely you are going to produce an induced EMF. Okay. Beyond the circular region, R or R more than R naught, we assume B equals 0 at all time. Okay, this one we already find we actually prove it because B equals to mu naught 2 pi I over R, because okay, the magnetic field going to be decreased with the increase of distance. Okay, but now because of the change of the magnetic field is going to induce an electric field, so we need to find the relationship for the R less than R naught and R more than R naught. Okay, so I proceed first with the R less than R naught. So basically you can actually refer to this picture. So the dashed line over here represent our closed loop for R, and R naught is basically the full radius. Okay, so based on the formula itself, which is closed loop EDL equals to negative d flux B over dt. Okay, so if you so means we can only focus on the magnitude. We can actually ignore negative over there. So okay, because is a closed loop, the closed loop is circle, so means that our E going to be constant. Okay, so we can actually remove E here outside, so we are going to get E integrations of EDL d flux V over dt. So you are going to get here the DL is one circumference is 2 pi R, and here you are going to get, so E equals to pi R equals to, okay, the area is doesn't change here, the area doesn't change, so the only things change is B. Okay, so you are going to get A dB over dt. Okay, rate of change of magnetic field. So E equals to 2 pi R equals to pi R square dB over dt. So pi can be cancelled out, R here, so you are going to get your electric field, induced electric field is R over 2 dB over dt. Okay, got it? Okay, so now we are going to find for the next one, which is R more than R naught. Okay, R more than R naught. Okay, R more than R naught. Okay, so the same thing, because you have a change in the B, the magnetic field, you are going to induce electric field. So we are going to use the formula for, okay, closed loop EDL equals to d flux B over dt. You can actually put negative over there, it doesn't affect anything, but if you feel not sure, you can actually put the negative over there. Okay, so E going to be constant because of what? Because the closed loop for R more than R naught, definitely we are going to choose the sphere, no, the circle. Okay, so here is the and then we are going to choose here, so this is going to be R, this is going to be R naught. Okay, so why we choose the circle shape is because we want to maintain our E here. Okay, so you're going to get E integrations of dl, same goes as this one, A dB over dt. Okay, here integrations of dl, you're going to get L, and the only area that have a change of magnetic field is going to be 2 pi R naught. Okay, please remember that this formula is the formula this part only going to focus only on the part that have the change of the magnetic flux. So the maximum area is going to be up until R0, this one. Okay, so that's why you put 2 pi R0 instead of 2 pi R. Okay, because this area is the maximum area that have a change of the magnetic flux. Okay, so this area is for area of the closed loop, so that's why you're going to get pi R square dB over dt. So E equals to, you are going to get R square over 2R dB over dt. Okay, understand? Oh, sorry. Okay, so what about the formula? Okay, so we are going to see the formula from the equations that we derive. Okay, so this one and this one. Okay, so the graph that we are going to get, E versus R. So basically inside this what it calls a circular area, the electric field is basically directly proportional up until R0, and here is inversely proportional. So you are going to get that graph. Okay, understand? So if you encounter the questions where you need to find the change of the B and relate with the induced EMF, you need to use this formula. Okay, so let's proceed to the next one. Okay, so here I have a test process 1. Okay, and then there's a lot of, I think there's 4 questions at the back. Okay, please do it by yourself, and I actually provide you with the answer. Okay, so this is the questions for the magnetic flux. It's better for you to draw to make sure that you know the directions, to make sure that you know the directions of the magnetic field and the directions of the normal area to the plane. Okay, please take note, flux BA cos theta. Theta is basically the angle between B. Okay, example, you have like this object. Okay, and A, the normal to the A is always perpendicular, sorry. Okay, so the B here, example, this is your B, this is B, and this is angle. Okay, so the cos theta here is basically represent B and the normal to the area. Okay, and your normal to the area always outward, like we learned in the Gauss law before. Okay, so you can answer this question also to make sure that you understand the magnetic flux. Over there, I already show you the working step. If you have any question, feel free to ask in online teaching. Okay, same goes to this one. This question is basically also about the magnetic flux. No, it's about the change of the magnetic flux, and the question asks you to find the average EMF that will be induced in the wire loop during the extraction process. So these questions, definitely you are going to use the formula EMF equals to BLV, and then if the coil is viewed looking down on it from above, is the induced current in the loop clockwise or counterclockwise? So when it comes to the question asks you about the induced current, you need to find the directions of the original magnetic field first. So directions of the original magnetic field is positive Z direction. Okay, so and then the next information that you need to know is whether it's increase or decrease. Okay, so if the loop is removed from the field, okay, so example, you have a area of area like this, a plane of the magnetic field, and then you have a loop. over here, so it's removed. So when it's removed, it means that decreasing of the magnetic flux. So means that when you use the first thumb rule, decreasing, for you to find the induced current is going to be in the same direction. Okay, same direction. So means that is going to be, answer is what? Counterclockwise. Okay, got it? Okay, next. Okay, this question asks you to find the induced entropy at the point near the center of the solenoid. Okay, the question asks you to find the di dt. Okay, so I'm going to show you for this one only. I can already show you at the back. I have the working step at the back. Okay, okay. So these questions, you are going to use the formula of the. Okay, you're going to do. Okay, first thing first. You can see that you have a thin solenoid. So remember, when it's about thin solenoid, there's a one formula that magnetic field related to the solenoid, which is B equals to mu naught small n I. Small n is number of loop per unit, not unit volume, is basically is per length. Okay, so the original is mu naught n I over L. Okay, so now because the question asks you to find the change of current here, change of currents, the increasing of currents, so definitely you are going to use the formula of the induced EMF. Okay, so you are going to have a formula E dl negative d flux B over dt. Okay, so long thin solenoid. Okay, long thin solenoid, so we are going to maintain our E here, the current. Okay, E here. Okay, means that you have a solenoid, so your eyes is in this direction. Okay, yeah, wait, no, sorry, okay, so means that we are going to maintain our E. So E going to be the closed loop of dl equals to, so it's going to be equals to area going to be the same thing because the solenoid going to be constant in terms of its shape, so dB over dt. Okay, because the change of the increasing okay, because the IDT, definitely you are going to have induced EMF, which means that you are going to have the change in terms of magnetic field over there. So you put this formula into this one. Oh no, sorry, this formula into this one, because the question gives you 400 turns per meter, so this is basically N. Okay, so you're going to get E, the integrations of dl, you're going to get 2 by r. So area, so you're going to get mu naught n a di over dt. Okay, okay, rearrange all the formulas for us to find the di over dt. So di over dt means E equals to 2 by r, so mu naught n e. Okay, so use this formula, put and then insert all the numbers over there, then you are going to get the answer. Okay, so okay, so the answer is going to be 9.207 amperes over seconds. Okay, okay, so as you can see that here we have, okay, so 2 pi r here is the where the change of the magnetic flux occur, and then area here is the area where the question asks you to find it. So here they already give it to you to find the 3.50 centimeter from its axis. So this one going to become E equals to 2 pi r. No, sorry, hold on. Wait a second. Okay, so it's going to be E 2 pi r mu naught n pi R square. R here is basically the area that the question asks you to find the change of the rate of change of current. So pi can be cancelled out. So the final formula going to be di over dt equals to E to R over mu naught and number of loop per unit length, and then R square. R square is basically the capital R is the area that the question asks you to find, the radius the question asks you to find it, which is the closed loop. Okay, so okay, you can refer to the working set at the back, okay, and then you can actually ask me during the online teaching. Okay, so this is all the working steps for the previous question. This one also, and this one already show it to you. Okay, so you can actually refer to these questions, to this answer. Okay, let's proceed to the next one. Okay, generator and motor. Okay, so here this is the crucial part. Okay, the crucial part where you need to understand the AC generator, how to produce an AC current, how to produce a DC current, how basically a generator and motor works. Okay, so first thing first, I'm going to explain in terms of AC generator. Okay, when it comes to the AC generator, we are going, okay, there's a closed loop over here, loop over here. They're actually inside the magnetic field. Okay, and then here you can see that we use 2 slip ring, okay, for the AC generator. For the DC generator, we use not slip ring, we use split ring. Okay, and then this slip ring is basically connected to the external circuit. Okay, so how is produced an alternating current? Okay, so you can need to understand that when it comes to the alternating current, the directions of the current always change. Is going to be sometimes rotate clockwise, sometimes rotate counterclockwise. Okay, half circle is going to rotate clockwise, half time is going to rotate clockwise, half time is going to rotate counterclockwise. Okay, so it's in front of you. I already show you the diagram, but I'm going to show you once more. Okay, so okay, so we have armature, or we call as a loop. Okay, and this loop is basically connected to the slip ring. Okay, so we have 2 slip ring over here. Okay, so this slip ring, 1 slip ring, and then there's a brush over here. Okay, and then there's another one slip ring, and then we have a brush over here that is going to be connected to the external circuit. So example, this one we are going to connect it to the ammeter. Okay, so example, this is ammeter. Okay, so yes. Okay, and then we have here is a magnetic field, so north and south. So definitely the directions of the magnetic field is moving from the north to south like this. Okay, I'm going to show it to you how the current actually produced inside the generator. Okay, so as you can see that when it comes to the generator is basically produce is basically convert from mechanical energy into electrical energy. This mechanical energy, it can be like steam turbine, it can be like falling water, it can be any mechanical means to move the loop here, or we call as the armature. Okay, armature. over there. Okay, armature, ARMT. Okay, alamak. Why I cannot write here? Okay, armature. Okay. Okay. So using okay, so you can see that when this thing when this loop or armature actually rotate, is going to change the magnetic flux. Okay, they're going to change a magnetic flux. Okay, when it changes the magnetic flux, definitely they're going to have a induced current. So right now we need to find the directions of induced current produced inside this AC generator. Okay, so for this one, when it comes to the induced current, you need to use the okay, you can actually use the right hand rule, but you need to change. Okay, before this we use FIB, right hand rule, right? Okay, I'm encouraging students to use left hand for the induced current with the same FIB. Okay, so same F perpendicular to the I, perpendicular to the B. Okay, so the force going to be the thumb, the second finger is going to be your current, and the middle finger going to be your magnetic field. Okay, I'm using the left hand. Okay, if you want still stick to the right hand, you need to change it to the FBI. So it means that you're the thumb. Okay, for the right hand. Okay, this is right hand rule for the induced current. F, okay, the force not going to change for the thumb. For your second finger going to be your magnetic field, and your middle finger going to be your currents. Okay, but I'm encouraging students to make sure that there's not confused. So for the induced current, it's better for you to use the left hand side, but make it as a FIB also. Okay, so now example, if the loop going to be rotated by mechanical means. Okay, so example, if example is rotated in clockwise direction, so I put it as A, B, C, and D. Okay, so means that we need to find the directions of the current here at the A and B. Okay, so the A and B, the force going to be upward because it's rotate clockwise. Okay, so use the left hand rule, rotate clockwise. Okay, and your magnetic field is north to the south. So the directions of the induced current going to be, yes, very good, it should be there, inward. Okay, what about C and D? Okay, same thing here. Force now going to be downward because it's rotating clockwise. Okay, so be downward, and your north to south magnetic field, so you are going to get, your directions of this current going to be upward. So this is connected, and then what happened is going to move inside the external circuit, which means that moving in clockwise motion. Okay, so directions of the emitter going to be in this direction. Okay, so when you have the half time, okay, I'm going to put it now. Okay, when you have a half time here, okay, the proper diagram is basically here. Okay, but I'm going to show you how this thing changed for the AC current. Okay, so example, okay, the same thing here, I'm going to show it to you. Okay, you have armature connected to the, and okay, right now is a half time. Okay, half time means that the A and B, C, and they already changed their position. Okay, so I'm going to put it like A and B, C and D. This is C and D. Okay, this is C, D. This is A, B. So it means that is going to be like diagram here. Okay, and then it's going to connect it to the slip ring, and then the brush over there is going to be to connect it to the external circuit, and here is going to have a brush here. slip ring and going to connect it to the external circuit, which means that we are going to use the ammeter. Okay. Okay, so definitely we need to have a magnetic field over there. Okay, so this is north and this is south. The directions of the magnetic field always be from north to south. Okay, so now, okay, it's still moving is still moving clockwise motions, but the in half time the positions of A, B, and C they already changed. So means that we need to find a current, induced current inside the armature or loop first. Okay, so so this one moving clockwise, so this is going to be output for the force, and A, B going to be downward. So use left hand rule to make it easy, FIB. Okay, FIB. So the directions of the current here going to be like this, which is inward, and this one going to be outward. So when it's connected to the external circuit, you can actually find that it's moving in the counterclockwise. Okay, like this is clockwise. Okay, so basically the change, okay, so it means that it's going to be in this direction. So basically inside the armature, the directions of induced current doesn't change, but when you actually connect to the external circuits, the slip ring of there are going to cause the change in terms of clockwise or anti-clockwise. Okay, so the proper diagram I'm going to show you after this, so you can actually understand how it happens. Okay, but for the proper diagram here, I draw it for you already. Okay, so this is basically the one. Okay, so that's why you are going to get AC moving in different direction for every half time. Okay, and then for this one, you can actually see that this is basically the movement, which means that the A, B, and C they already changed for half time. So the directions of the currents moving like clockwise, and then it's going to change anti-clockwise, and then change to clockwise again, and then counterclockwise. Okay, so this is the full diagram, but the real diagram of the generator I'm going to show you after this. Wait. Okay, so basically this is the real picture of the diagram. Okay, it looks 3D, which is more better than mine. Okay, but it's okay. So you can see that here the right now it's moving in clockwise motion. So what happened here is, using the right hand rule FBI or left hand rule FIP, you are going to get your force, your currents, the induced current in this direction. Okay, so when you actually connect to the slip ring, is moving now here, you can actually see that it's moving in clockwise motion. But once half circle, when C and D and A and B change already, which is you can see from the next picture, the induced current inside the armature still in the same direction. However, you can see that this one connect to this one, so is moving in the counterclockwise motion. So basically what happened here is the change of AC current affected by the slip ring outside, because this one, okay, because this one directly connect to this one. Okay, and for this one is connected to the first one first, and that's the reason why it's moving like this. Okay, so okay, got it. Okay, let's proceed to the DC generator. Okay, DC generator is very easy. Okay, it doesn't change in terms of direction, it's moving in one directions only. Okay, so the difference between DC generator and AC generator is in terms of split and slip ring. Okay, for the DC generator, the armature is basically connected to only one, we call it a split ring. So it's going to be like, wait, it's going to be like this. Okay, this is connected like this, and then it's going to be emitter. Same go, this is we call as the slip ring. Okay, this one we call a split ring. Okay, the what we call the AC generator, we use slip ring. Okay, this is AC, this is DC. So basically what happened here is the directions of induced current, you are going to decide as the same as the AC generator. Okay, because DC generator also convert from mechanical to electrical, so north to south. So this is directions of magnetic field. Example is moving in clockwise motion. So this is A and B, C and D. So the directions of the current for the AP going to be you use right hand rule FBI, or you use left hand rule FIB. Okay, north south. So this is going to be in this direction. So means that this going to be always in the directions of clockwise motion. Okay, because it's only connected to the one part only of this split ring. That's the reason why it doesn't change in terms of direction. Okay, so that's the reason why you are going to get the DC generator is only in one direction like this. The graph going to be like this. However, for the AC generator, you are going to get is basically like this, EMF time. Okay, okay, so this is the graph for the AC generator. So we need to find the formula for the AC generator. Okay, so as you can see that I hope you still remember about the angular frequency. The angular frequency is omega. Okay, angular frequency, okay, because it's moving with some angle. So angular frequency, basically our angular velocity is angular displacement divided by angular of time, rate of change of angular displacement. Or you actually can remember theta equals to theta naught plus omega t. Okay, the first angle going to be 0. Okay, so you are going to get theta equals to omega t. Okay, so how to get the formula for MBA omega sine omega t? Okay, so first thing first, you use the Faraday law, negative d flux B over dt. Okay, so B, so the magnetic field B and area A doesn't change. The only things change is in terms of angle, because the armature always rotating 0 degree, 30 degree, 90 degree, something like that. Okay, so that's why here we are going to change a little bit our formula. You're going to get here negative BA d over dt cos theta, because basically flux is BA cos theta. Okay, so theta here, you put this one, you are going to get negative BA d over dt. So you are going to get cos omega t, differentiate of cos omega t, you are going to get negative BA omega negative sine omega t. So negative over there cancel out, so you are going to get BA omega angular frequency sine omega t. Okay, okay, so because as you can see that for the armature it contains a lot of loop, so that's the reason why we need to change our formula. EMF equals to number of loop MBA omega sine omega t. Okay, and this is the formula. Okay, that's how you get the formula. Okay, okay, so please remember also, if example the questions give you frequency, for you to find the omega, you need to use omega equals to 2 pi f. Okay, okay, so this is for the AC generators. Okay, because that's the reason why you can see that minimum and then maximum, minimum and then maximum back, because at the next part, why is become minimum and maximum, I'm going to show it to you. Okay, so let's move to the next one, how we get maximum or minimum, okay, because this is the very important for you to understand. Okay, so you can see that why is become maximum and minimum. Okay, so basically at the first part, the loop going to be in this direction, okay, which mean the example, if we have like, oh my god, where is it, okay, wait. If example, the magnetic field or the magnetic field that passing through is 4. So what happened here is, when it comes to this kind of change, is going to have a change of the magnetic flux, so means that that's the reason why they have an induced current. Okay, and then why this part is become maximum is because of there's no more magnetic field that passing through a loop. So from 0 degree to 90 degree, it means that from 4 magnetic field to nothing magnetic field is going to cause you a maximum of the induced EMF of induced current. And the reason why you are going to get this part, the maximum part, okay, which you can see that from this picture, the above picture. So this one have 3 magnetic field, and then suddenly there's no more magnetic field passing through a given area because the perpendicular is N here, the perpendicular of it is going to be N here, okay, and this is B, so it's going to be cos 90 degrees, so it's going to be 0. So, but that's the reason why they're going to get maximum. And however, when it's going to rotate in the original position but change A, B, and C, D, the same amount of magnetic field passing through, that's the reason why it's going to get 0. It means that there will be no induced current. Okay, so when change into the position of the cos 90 degree, then it's going to be a maximum again. Okay, so the amount of magnetic field passing through a loop, if it's constant before and after, is going to cause you a 0 induced EMF, no change. Okay, because you need to understand that for the induced current to produce, they definitely need to have a change of the magnetic flux. Okay, so it means that the amount of magnetic field passing through a given area. Okay, and that's the reason why you get this sinusoidal shape for the AC generator. Okay, got it? Okay, so here 30 degree is not the maximum. It means that it's going to be maybe here the induced EMF not maximum, but induced EMF going to be maximum when there's no there's a from a maximum there's a like magnetic field, you have 4 of it passing through a loop, and then after that there's no more, and there's going to be a maximum value. Okay, got it? Okay, let's move to the next one. Okay, wait for a second. Okay, so this one, the question is very easy. This is our direct question. The question asks you how many loops must the coil contain if the P output is to be EMF 170P. So you are going to use, when it comes to AC generator, you are going to use EMF equals to MBA omega sine omega T. But the question asks you without in terms of time, so you can actually ignore this one. So here omega, you use 2 pi f because the question I give you 60 hertz. Okay, please take note that in Canada and US, they basically use the frequency is 60 hertz. Okay, 60 hertz for Canada and US, but other country they are going to use 50 hertz, the angular frequency. Okay, what does it mean by frequency? The number of the amount of. Okay, so frequency is basically a number of cycles in 1 second. Okay, that's a frequency, number of 1 cycles in 1 second. In 1 second. Okay, so this answer for these questions, supposedly you are going to get 150 terms. Okay, let's move to the next one. Okay, so this one is basically to show you the difference between AC generator and also DC generator. Okay, So the difference is going to be in terms of slip ring, and this is split ring commutator. And the directions of the induced current there is basically for AC generator is always keep changing, and DC generator always in one direction. Okay, make sure that you understand how to produce an AC generate AC current, because it's going to be asked in your exam. Okay, so it's better for you to fully understand, because after this in chapter, if I'm not mistaken, next chapter, we are going to use AC current as our formula. Okay, so please make sure that you fully understand for this part. Okay, if you didn't understand, feel free to ask. Okay, next, motor. Okay, motor difference from the generator. Okay, so motor is basically convert mechanical energy to electrical energy. So means that when it comes to the motor, we provide a current to them. So means that now we need to find the directions of rotational of armature, whether it's clockwise or anti-clockwise for this one. Okay, we need to find it. Okay, so for this one, you need to use a normal right hand rules. Okay, so example lah. Okay, example, I didn't give it to you this one. Okay, so we need to find by ourselves the directions of the force at this part, and at this part, whether it's upward or downward. So now we are going to understand whether it's moving clockwise or anti-clockwise. Okay, now first thing first, you need to draw the directions of current here. So there will be a plus here, so currents, conventional current moving from positive to negative. So it's going to be in these directions. Okay, using your right hand rule, which is FBI, it should be FIB. Okay, so you are going to get, okay, north to south in this direction. Okay, so north to south, FIB. Okay, and then currents over there is there, so means that this one going to be force downward, and this one force going to be upward, and that's the reason why it's moving in clockwise motion. Okay, make sure that you use the normal right hand rule. Okay, right now the missing things is force. Why force? Because we want to know about torque. Okay, it's moving in circular motion. Okay, so we have current, and then we have a magnetic field over there, so we can actually find force using normal right hand rule. Okay, got it? Okay, good. Okay, however, as you can see that when it comes to motor, okay, current produced by external part, okay, which means that here, and it's moving in clockwise motion. Okay, because current is produced, and then and this armature is going to rotate. So what happened is when it actually rotate, it's going to change, it's going to cut a magnetic field, which means that there will be a change of magnetic flux, right? And this change of magnetic flux is going to produce what? Induced current, induced EMF, which is induced, as if induced EMF, induced current. So this induced current going to produce what? Induced magnetic flux. And what is the function of the magnetic flux? To oppose the original change in the magnetic flux. So means that you can actually see that when the produce magnet when this thing produce when the induced current produce a magnetic flux that oppose the original change, the change means that it's going to oppose the original change of the loop, which means that now the current is basically means that what happened is going to produce a drag torque, or we call as a back EMF. Okay, this back EMF and drag torque is basically to is going to cause a resistance in the motions of the armature. Okay, because the change of magnetic flux produce induced current, and this induced current going to produce a magnetic flux that oppose the original change in the magnetic flux. So this induced magnetic flux is basically going to produce a drag torque or back EMF. Okay, so what happened is the movement of the armature not going to be that smooth, it's going to have some resistance. Okay, okay, so okay, okay, so I already explained here how the drag torque or back EMF actually produced. That is creating this retarding torque is commonly known as the counter torque, or we call as a drag torque, or another name is back EMF. So greater induced electric current produced, greater counter torque is. So means that, example, if you you have a current, okay, external circuit produce a current. Okay, this current actually going to cause the rotational motion of the armature, okay, whether it's clockwise or anti-clockwise. So but this one is going to be so smooth because there's going to be a counter torque that's going to oppose. Example, if your armature moving in clockwise, the counter torque going to move in the other way around. Okay, so that's the reason why there going to be like some energy going to be lost here. Okay, okay, basically it also happens inside the electric generator. Okay, see, so for the electric generator, we actually produce induced current. Okay, okay, we produce induced current. Okay, okay, but this induced current itself also produce their own magnetic flux. They're going to oppose the original change in the magnetic flux. So it means that the generator itself also will have a counter torque. Okay, so it means that the movement of armature for the generator and the movement of armature for the motor going to be not that smooth because you are going to have a counter torque, and this counter torque basically produced from what? From induced current, because induced current produce the magnetic field that oppose the original change. Okay, okay, so basically for the motor itself, if example, if you have load, okay, if you don't have any load, okay, so what happened is the motor speed will be increased, and same goes as the back EMF, or we call as a drag torque, also increase. So motor increase by EMF is going to be equal. However, if we have a mechanical load motor, what happen is the speed of the armature, or we can the speed of the loop, going to be decreased. Therefore, your back EMF also decrease. So you can actually conclude that the greater the mechanical load, the slower motor rotate, or here our armature rotate, and therefore is going to lower the back EMF. Okay, so basically what happened is motor and generator both basically produce a counter torque, or another name is a back EMF, or another name is drag torque. Okay, okay, so here you have a questions in front of you, basically a motor, and the armature winding of the DC motor have a resistance of 5 ohms. The motor is connected to a 120 volt line, and when the motor reach full speed, okay, basically the back EMF going to produce when your speed is more than your normal speed, mostly. Okay, but basically means that the back EMF going to affect a lot when you have a speed more than normal speed. Example, if your speed is lower than your normal speed, your back EMF going to be lower, so it's not going to be affect more. Okay, so that's the question. That's the reason why the question state reach full speed again is normal load. The back EMF, which is the counter torque, is produced is 108 volt. calculate the current into the motor when it's just starting up. Starting up means that at that particular time, the back EMF itself is quite small, so we can actually ignore. So for this one, we can use only V. Okay, so for this one, we are going to use only V equals to IR. So you need to find the current over there, V over R. Okay, so right now you doesn't have to like minus with the back EMF, because back EMF is very small. However, when the current motor reach full speed, definitely your back EMF going to be increased and it's going to affect your voltage. So you need to find the remaining voltage towards the DC motor, which means that now your original is 120 and your BMF is 108. So you only have 12 volt for you to operate a DC motor. So based on the Ohm's law, V equals to IR, I equals to V over R, which means that the potential, the current is directly proportional to the potential difference. So the smaller V going to affect your current, which means that based on the V equals to IR, your I here going to be get 2.5 ampere. In compare with the first question, you get 24 ampere. So why is become smaller? Because you have a back EMF. Okay. So basically, the real life application is when you actually start your car. If you realize that when you start your car, the intensity of light of your headlights is like higher, but after a few seconds it become dim. Why? Because at the first start, when you actually when you start the car, your back EMF is very smaller, so the voltage over there is bigger. It doesn't affect by the back EMF. However, after a few seconds, when you have a full speed which is more than your normal speed, then your back EMF going to be higher. So that's the reason why your headlights after a few seconds going to be dim. Okay, because the voltage, the remaining voltage is smaller because affected by what? Counter torque or back EMF. Okay, got it? Okay, let's proceed to the next one. Okay, the next one is basically the summary of the chapter 11. Okay, so here you need to make sure that you understand about how the induced current basically produce. Okay, so which means that is going to be relate with the Lenz's law. Okay, and then it's going to relate with the Faraday law. Okay, so this one is Faraday law, which means that is going to affect by the change of the magnetic flux. What does it mean, magnetic flux? It means that the magnetic field passing through a given area. So when you have a change of it, you are going to induce some EMF. Okay, so this is the formula for the Faraday law, which means that when you have induced EMF, as if you have induced EMF, you are going to have an induced current, and this induced current going to produce magnetic field that oppose the original flux change. Okay, that is going to be inside for the Lenz's law. Okay, other than that, you need to understand also the change of the magnetic field also not only produce induced current, is basically also produce electric field. So that's the reason why you are going to have this formula EDL d flux B over dt. And then here also we talk about, we have AC current, and then we have DC, we have AC generator, we have DC generator, and then we have motor. Okay, please take note, when it comes to the AC generator, make sure that you use the left hand rule, but you still stick to the FIB. But when it comes to the motor, you use right hand rule, FIB also. Okay, it's much easy for you. Induced current, use left hand side, right? The monomal current, use right hand rule. Okay, and then make sure that you understand how the AC generator works, how DC generator works, and how motor works. And don't forget to understand how the back EMF produce. Okay, so the last one going to be the questions. Okay, this question you can, you need to do it by yourself, and then make sure that you know how to change revolutions. Okay, so for this question, you need to change first 1000 revolution per minute into what we call as the radian per second. So how to do these questions is practically easy. Okay, but you need to read the question carefully, okay, because the question state here, the alternator is gear here. The alternator is geared to rotate 3 times for each engine revolution. Means that for one engine, 1 times is 1000 revolutions, so you need to multiply by 3. Okay, so 1000 revolution per minute is 1 revolution is 2 pi, and 1 minute is 60 seconds. So you are going to get 7 times 2 pi divided by 60. You're going to get 104.7 radian per second. Okay, but because it's 3 times for each engine revolution, so times 3, you are going to get 314.2 per seconds. Okay, radian per second, which is this is going to be your omega, angular speed. Angular speed is omega. Okay, so based on the equations, which is mb emf equals to mba omega sine omega t. Omega we already find, so we need to find here to find the induced emf in the alternator as a function of time. So this is the epsilon naught. So n is 250 times BA is basically flux. So the original flux is here, 2.50 times 10 to the negative 4 Weber. Okay, so it's become 2.50 times 10 to the negative 4. So the omega is 314.2 sine 314.2 t. Okay, so you are going to get 19.63. So because it's as a function of time, you need to make sure that you give your answer in the sine omega t or on sine omega t. So EMF, the induced EMF, going to be 19.63 volt sine 314.2 t. So you're going to get this answer. So for the maximum EMF here is going to be 19.63. Okay. Okay, so I forgot to mention that the epsilon naught is not the original one. The MBA omega, the epsilon naught is the maximum. So when it becomes, when you have a graph here, EMF naught is basically here the maximum pi. So the question asks the maximum EMF, and that's the reason why you use MBA omega sine omega t. Okay, so that's how you do it. So please understand this chapter. This chapter is chapter 10, so we are going to proceed for the next chapter, which is something that induce also. If you have any questions, feel free to ask during online teaching. So thank you very much, and I'm going to see you again. Bye. Assalamualaikum.